Segment 1. You have been lied to your entire life. Nothing can travel faster than light. You've heard that sentence so many times it feels like one of the laws of reality itself. But what if I told you the universe is already breaking that rule? Right now, at this very moment, there are galaxies moving away from you faster than light. Not almost as fast, faster. So was Einstein wrong? Not even close. The real surprise is that almost everyone misunderstands what Einstein actually proved. The speed of light isn't simply a speed limit, it's a speed limit with a loophole so strange that it forces us to rethink what motion even means. Today, we're going to explore that loophole, from the strange geometry of spacetime to warp drives, wormholes, and the biggest obstacle standing between science fiction and reality. By the end of this journey, you may discover that going faster than light isn't about building a faster spaceship. It's about changing the road beneath it. Segment 2. Let's begin with the rule everyone knows. Imagine you're driving down a perfectly straight highway. You press harder on the accelerator. The engine roars. The scenery rushes past faster and faster. Everything about your intuition tells you that if you keep adding enough power, eventually you'll reach any speed you want. The universe doesn't work that way. According to Einstein's special theory of relativity, every object with mass becomes increasingly difficult to accelerate as its speed approaches the speed of light. It's almost as if the universe keeps adding invisible weight to your spacecraft. Every extra kilometer per second costs more energy than the one before. At first, the increase is tiny. Then it becomes dramatic. Closer still, it becomes almost impossible. Imagine trying to push a shopping cart across a smooth supermarket floor. At first, it glides effortlessly. But with every meter, someone secretly loads another 100 kilograms into the cart. You keep pushing harder, yet it barely accelerates. Eventually, every push accomplishes almost nothing. That invisible loading process is remarkably similar to what happens when an object approaches light speed. The closer you get, the more the universe refuses to cooperate. This isn't because your engine fails. It's because space and time themselves begin changing around you. And that changes everything. Segment 3. To understand why, we have to stop thinking of space as empty. Most people imagine the universe as an enormous box. Stars float inside it. Galaxies drift through it. Space is just the stage where everything happens. Einstein saw something completely different. Space isn't the stage. Space is part of the performance. Imagine stretching a giant rubber sheet across an entire football stadium. Place a bowling ball in the center, the sheet bends. Roll a marble nearby, and it doesn't move in a straight line anymore. It curves toward the bowling ball, not because an invisible hand pulls it, but because the surface itself has changed. Gravity works in much the same way. Mass bends space-time. Planets don't constantly fire rockets to stay in orbit. They simply follow the curved geometry surrounding massive objects. This idea sounds abstract until you realize your GPS depends on it every single day. Satellites orbiting Earth experience time slightly differently than clocks on the ground. Engineers must correct for this effect continuously. Without Einstein's equations, your navigation could drift by several kilometers every day. Relativity isn't an exotic theory locked inside university textbooks. You're already using it, whether you realize it or not. Now here's where things become truly strange. If gravity can bend space, could space itself move? At first, that question sounds meaningless. How can space move if everything exists inside space? But the universe has already answered it, and the answer shocked cosmologists. Segment 4. Around 100 years ago, astronomers noticed something unexpected. Nearly every distant galaxy was moving away from us. At first, some people imagined Earth sat at the center of a gigantic explosion. It was an understandable mistake, but the data kept improving. Soon they realized something far stranger was happening. The galaxies weren't racing through space. Space itself was expanding. Imagine drawing tiny dots across the surface of an uninflated balloon. As you blow air into the balloon, every dot moves farther away from every other dot. None of the dots are crawling across the rubber. The rubber itself is stretching. The expanding universe behaves in almost exactly the same way. Galaxies are like those dots. Space-time is the balloon. Here's the incredible consequence. If two galaxies are separated by enough expanding space, The distance between them can increase faster than light. Read that again. The universe itself allows distances to grow faster than light without violating Einstein's speed limit, because nothing is actually racing through its own local piece of spacetime faster than light. The road is stretching, not the car. That single distinction is one of the most important ideas in modern physics. Einstein never said spacetime couldn't expand faster than light. He said objects cannot locally travel through spacetime faster than light. Those are completely different statements. And inside that difference lies one of the boldest ideas ever proposed by theoretical physics. Instead of making the spaceship move faster, what if we made spacetime move instead? Segment 5. Now we arrive at the idea that transformed faster-than-light travel from pure fantasy into serious theoretical physics. In 1994, physicist Miguel Alcubierre asked a question almost nobody had dared to ask. If spacetime itself can stretch faster than light, could we engineer that process? Notice what he did not ask. He didn't ask how to build a faster engine. He didn't ask how to break Einstein's equations. Instead, he accepted every rule Einstein had written and searched for a loophole hidden inside them. Imagine standing on one side of a moving walkway at an airport. If the walkway begins carrying the floor beneath your feet, you travel across the terminal without ever running. Now replace the airport floor with spacetime itself. That is the heart of the Alcubierre warp drive. The spaceship never outruns light through its local region of space. Instead, the region of space surrounding the ship begins moving. Think back to our highway analogy. Until now, you've been trying to build a faster car. Alcubierre suggested something completely different. Forget the car, move the highway. Imagine the road behind your vehicle continuously folding forward underneath the wheels while the road ahead shrinks toward you. From your perspective, you're barely moving, but to everyone watching from far away, entire light years disappear beneath your ship. You didn't drive across the road, you brought the destination closer. That's the fundamental difference. The ship stays inside its own small bubble of ordinary spacetime. The bubble is what travels. Segment 6. So what would that journey actually feel like? Surprisingly, almost nothing. If you've ever watched science fiction movies, warp travel usually looks violent. Alarms sound, crew members struggle to stand. Stars stretch into bright lines across the windows. Real relativity predicts something much stranger. Inside a perfectly stable warp bubble, passengers might feel completely at rest. Imagine sitting inside a train with perfectly smooth suspension. You place a glass of water on the table. The train begins moving. As long as it accelerates gently enough, the water barely ripples. Close the curtains. Without looking outside, you can't even tell you're moving. A warp bubble pushes this idea to an extreme. Everything inside the bubble shares the same local space-time. Your heartbeat doesn't suddenly race. Your body isn't crushed against the seat. Your coffee doesn't splash across the cabin, because locally, nothing extraordinary is happening. The extraordinary motion exists outside your bubble. Space in front contracts. Space behind expands. The bubble simply rides that changing geometry. It's one of the strangest consequences of general relativity. The passengers don't travel through space. Space carries the passengers. Segment 7. But how exactly would space move? This is where our highway analogy becomes even more useful. Imagine a long strip of elastic road stretching to the horizon. Normally, driving from one city to another means crossing every kilometer in between. Now imagine someone standing ahead of you, grabbing the highway, compressing hundreds of kilometers into only a few meters. At the same time, someone behind you keeps stretching the road outward. You continue rolling gently forward. Yet the destination reaches you astonishingly quickly. This is essentially the mathematical picture behind a warp bubble. The front of the bubble continuously contracts space-time. The rear continuously expands it. The spacecraft itself remains inside a region where physics behaves almost normally. If you drew the entire journey from outside, it would look almost impossible. The ship appears to cross enormous cosmic distances, yet according to the passengers' own clocks, they never exceeded light speed within their immediate surroundings. Einstein's local speed limit remains untouched. The geometry does all the work. Once you begin thinking this way, an astonishing realization appears. Movement isn't always about motion. Sometimes, Movement is about geometry. Segment 8. At this point, it sounds almost too perfect. No crushing acceleration, no violation of relativity, no faster-than-light engine. So why aren't scientists already building one? Because we've ignored the most expensive part of the equation. Imagine designing the world's greatest airplane. The aerodynamics are flawless. The navigation system is perfect. Every calculation checks out. There's only one problem. The aircraft requires fuel that doesn't exist anywhere on Earth. That's the situation physicists face today. The mathematics describing a warp bubble is surprisingly elegant. The material needed to create one is not. According to the original Alcubierre proposal, the bubble would require something called negative energy density. This isn't simply a battery with negative numbers written on it. It's a state of matter or energy unlike anything we normally encounter in everyday life. Everything around you contains positive energy. Stars, planets, people, atoms, light. Negative energy behaves differently. In certain quantum phenomena, tiny regions can briefly display effects that resemble negative energy. One famous example comes from the Casimir effect, where quantum fields behave differently between extremely closely spaced metal plates. But these effects are unbelievably small, tiny, fragile, nothing remotely close to the enormous quantities the original warp calculations appeared to require. It's like discovering a single drop of water on Mars after hoping to find an entire ocean. Yes, the phenomenon may exist, but scaling it into a functioning warp engine is another challenge entirely, and that challenge has become one of the greatest puzzles in modern theoretical physics. Segment 9. If warp drives try to move the road, wormholes try to eliminate it altogether. Imagine opening a road atlas and placing your finger on two cities thousands of kilometers apart. Driving normally means following every twist and turn between them. Now fold the map until both cities touch. The distance across the paper hasn't changed, but the distance through the fold has almost disappeared. That simple trick captures the basic idea behind a wormhole. Instead of carrying a spacecraft across space, a wormhole connects two distant regions of spacetime with a shortcut. If such a tunnel could exist naturally or be built artificially, a journey that should take thousands of years might last only minutes. It sounds even more powerful than a warp drive, but nature is rarely that generous. According to Einstein's equations, wormholes can exist mathematically. The problem is stability. Imagine digging a tunnel through loose sand. The moment you remove the supports, the walls collapse inward. A traversable wormhole appears to suffer from the same problem. Gravity wants to crush it shut almost instantly. Keeping that tunnel open may require the very same ingredient that troubles warp drives. Negative energy. Once again, physics allows the idea. Engineering refuses to cooperate. That's an important distinction. Science fiction often treats impossibility and difficulty as the same thing. Real physics does not. Segment 10. Over the last 3 decades, physicists haven't abandoned the dream. They've refined it. New theoretical models have explored ways to reshape the original Alcubierre concept, reducing the amount of exotic energy the equations appear to demand. Some proposals even suggest that carefully engineered spacetime geometries might avoid parts of the original design altogether. These ideas are exciting, but excitement is not evidence. Today, no laboratory has produced a working warp bubble. No spacecraft has compressed spacetime. No telescope has observed an artificial warp field crossing the cosmos. And no one has built a traversable wormhole. That doesn't mean these ideas are worthless. History has repeatedly shown that mathematics often arrives decades before technology. Black holes were once dismissed as bizarre consequences of Einstein's equations. Gravitational waves remained theoretical for nearly a century before detectors finally measured them. Even the global positioning system in your phone depends on relativistic effects that once seemed absurdly abstract. The lesson isn't that every equation becomes reality, it's that reality has surprised us before, again and again. Perhaps the greatest mistake is assuming today's engineering limits define tomorrow's universe. They don't. They only define today's imagination. Final segment. So, can you really travel faster than light? If by that you mean building a rocket that outruns a beam of light, number. Everything we've observed says nature forbids it. But if you ask a different question, Can spacetime itself be manipulated so that distant places become nearby? Physics gives a far more intriguing answer. Maybe. That single word has inspired generations of physicists to explore some of the deepest equations ever written. Because the universe isn't simply a collection of stars and galaxies. It's a geometry, a fabric, a structure that can bend, stretch, ripple, and expand. The real breakthrough came the moment scientists stopped asking how to build a faster spaceship. They started asking how space-time itself behaves. And that shift changed everything. Remember the highway we began with. For thousands of years, every traveler asked the same question. How do I move faster? Modern physics asks a completely different one. What if the road could move instead? That tiny change in perspective transformed an impossible dream into one of the most fascinating areas of theoretical physics. Whether humanity ever builds a warp drive is still unknown. Perhaps the required energy will forever remain beyond our reach. Perhaps new discoveries in quantum gravity will reveal solutions nobody has imagined. Or perhaps the universe will continue guarding this secret for billions of years. We simply don't know. But science has never advanced by refusing to ask impossible questions. It advances by asking better ones. And maybe that's the greatest lesson hidden inside Einstein's universe. The speed of light was never just a limit. It was an invitation to understand reality more deeply. Because sometimes the greatest discoveries don't come from breaking the rules, they come from realizing you never fully understood the rules in the first place.